Welcome to the virtual Jboss. Today we have Sonny from Red Hat, who leads the Hibernate search project. So he's going to be talking to us about using Apache Lucene with Java EE. So thanks for coming, Sonny. I'll hand over to you so you can introduce yourself and kick off your talk.
Thanks, Paul. I'll share my screen. Is it there?
No, you can just see me at the moment.
It's saying I'm screen sharing.
Yeah, I wonder if it's the problem if it's on multiple monitors. Could be the multiple monitor problem. Oh, I don't know. Sorry, you are screen sharing. Sorry, yes, it is fine.
Okay,
you just need to switch your slides. There we go.
Okay. Hello, everyone. We're going to talk about how to interact with Apache Lucene from a perspective of developing Java enterprise applications. So I'm expecting you're familiar with the different specs and the concept of a container where your applications are going to be run. To quickly introduce myself, I work in the Hibernate team since several years now. I'm now leading the Hibernate Search project, which is one of the components of this talk. It's the integration between Hibernate and Lucene. But there are other ways of using Lucene as well, so I'm going to try to be a bit wider in perspective this time. I also contributed significantly to the Infinispan team, even though I'm not officially on that team. And I helped them start the Infinispan query project, which is also an integration with Apache Lucene, and the Infinispan Lucene directory, which is the storage capability component for Infinispan, so that you can store Lucene indexes in there. And well, since I'm in all these different open source projects, I also happen to contribute to WildFly, to JGroups, to Lucene itself, and several other projects which are in this same space. So what I'm expecting to talk about is really a very, very easy introduction to what Lucene is and why it could be useful. It's really surprising to see that like the Lucene community is very wide, is very thriving and successful, but in the world I'm living, like I see all these people in the Lucene community and all these other people in the Java enterprise community, and from my perspective it looks like there are two different worlds with very small spheres. And we will switch to an introduction to Hibernate Search, which is one of these key components to integrate the two worlds, and also how this all integrates within Infinispan and WildFly. WildFly is, of course, the popular application server we build in the community and sponsored by Red Hat primarily, but not only. And Hibernate Search and Lucene itself and all these capabilities and Infinispan, they're all bundled within WildFly, so they are available out of the box. You just need to know what it is about and how it can help you to get advantage of these components. Also, we're going to see what we're planning for the near future in this area, because there is a lot of active development still going on in these areas. So to start from a very, very basics, the main problem you have is you cannot really expect your customers or people going to your website to come to your website and say, hey, I want your book, the one you are stored in your database under this specific primary key. That's how most of our integration systems work. Like they expect some specific reference and a direct link to which strictly identifies which data you're needing, but that's really not how human interaction works. So any interface which is related to humans, and you have to approach this problem in a different way. So, for example, if you go to Amazon and you want to buy a book, you will get, this is the primary interface that you see in the website. You're not asked, of course, to enter the primary key in there. That would be nonsense, right? So how can you do that to solve these kind of problems? We all know, well, in SQL we have the like operator, which is probably the closest thing that we have to be able to solve this problem. The problem is how can the like operator really help you out for this? It's a very bad fit. Let's say that you want to refresh some of your history lessons and you want to read up on some specific chapter of history out of the Wikipedia. So how would that work if you had an interface which is working with like the most silly interface for this would be to have a system which accepts a query like this. So like, okay, if you tell me exactly what the content is of what you're looking for, word by word, I can give you that content, which is of course absurd because if you already know the content out of your head, literally all of the words in the exact same sequence how it's written in the Wikipedia, then the whole purpose of the Wikipedia would be pointless, right? So you could try a small improvement, like let's say that you just have to remember the titles. Okay, so at school from now on we were going to mandate that children have to learn out of their head all of the titles of the URLs of the chapters, not the actual chapters, but they need to strictly remember these titles. Like you cannot forget a single letter out of there or you'll be lost this information. You can try to be a bit more effective. You know, the like operator accepts wildcards, and you can try, okay, you know, I will give you 3 keywords. You give me these 3 keywords and we are going to search all of it, and you can be a bit smarter than that. You can add, you know, a bit of lower casing on top of it to make sure that, you know, even if you didn't remember exactly how the case was, if you're giving me 3 of these keywords, or maybe I just find a couple of them, then maybe we can still find the article for you. Well, the first objection here is, of course, well, from the perspective of running this on a database, it's going to be very slow. It's a very ineffective operation, but it's also, it's not effective from a computational point of view, but it's also not at all effective from the perspective of actually finding what you're needing. Of course, you cannot expect that a system like Amazon got to the level of success it had by having a query like that, implementing this text box, the primary interface with its customers, right? And there are other companies, you know, who might know a thing or two about search. They certainly don't use like operators on a relational database to find what you're looking for. And there are many other companies which might not have a primary accent on their, like Twitter doesn't really look like as a company who's based on search engines, but actually it is. It's primarily, their main business relies on their Lucene infrastructure. So they have massive amount of information which is completely indexed in Apache Lucene. There are well-known users of specifically Apache Lucene, not just any full-text search engine. And I'm not really sure how Twitter makes money or what their business model is, but it is very clear that we have a search text on top of the website, and they can give you things like search by specific keywords, like you have these hashtags and everybody talks about what's the hashtag is, and you have this concept of signals, like what's the most trending thing in a specific moments. These signals and these trend operations, they're all full text operations which are run on the index, and from there they can extract probabilistic information about, statistical information of what people are talking about. And what they're talking about isn't really about a specific string of characters, it's about concepts. So you have to do a bit of synonyms, you have to understand a bit of typos, and of course using hashtags specifically helps, but they can do much more than that, of course, if they have a Lucene index, and they have that. So am I cheating here? I'm I'm mentioning all these very successful companies who are based on full text search, but really, can you think of any very successful company which does not have some effective full-text search on their website? I think not, because if you find one, it's probably some kind of backend service company which does not interact directly with humans. Because if you're interacting with humans, the primary interface that you're having is really this kind of dialogue. The human doesn't really know what he's looking for, and he's going to toss you some keywords, some sentences in natural language, and the computer needs to guess what you want at that point. So, of course, to recap this, you cannot expect the people coming to you to type everything exactly or precisely because they are coming to you because they don't know exactly what they're looking for. You cannot put up a very complex form with many fields and say, you know, you have to fill up these 20 pages of forms in these fields exactly like that, because you need to, all these successful websites, they're all having this common thing of having one input text. And don't worry, we are able to figure it out because, you know, you're talking, you're expressing some language, so you're using keywords. Another common requirement is people are very used now, they're expecting websites to respond in a blink of an eye. Like if you're being slow when navigating your website and searching things is taking a couple of seconds, I'm going to some different website because I'm getting a much better experience there. And the most important one of all of them, and the reason why the like operator on SQL is really not a good fit, is relevance. So relevance is really this thing for which, when I'm looking for something, what I'm looking for needs to be on the top result right there. Now look at this page. I'm Googling for Hibernate on Google, and it's giving me some hints. Like, okay, we had 20 million results. That's, I guess it's an approximation, right? It's a bit of a wrong number, but from all these 20 million results, how would you like using Google if it was returning all these results like in alphabetical order? And then it's like, okay, and here are all the pages. You can go and find what you wanted out of there. It's like, that's nonsense. You really need to have, and people working in marketing, they know it nowadays, in the web marketing especially, you need to be in the top 4 essentially to be seen by anybody. If you're below that, you're invisible. People won't see you because we're so used to Google, and we expect the same kind of experience from any other service. So I'm typing something, I search for it, it has to be on top, or you're dead, essentially. You'll be eaten by competition. Of course, we have to consider some more complexity, like there might be some needs of more approximations. Some language analytics might be useful, like I'm going to massage your input because I understand it English, and so I can transform it, or maybe I understand that it is French or Chinese. And so how are we going to implement all of these different specializations of twists of languages? And one which I really find interesting is the concept of technical language and specialization languages. Like, that's a field in which you can provide something really, really clever in your application, and you will never get from something like Google, because Google is a generic search engine, while when you're building your own, and it has a specific purpose, you can train it, or you can inject knowledge about specific synonyms or technical knowledge or abbreviations. Like if you're building an application for medical applications, you can put lots of medical knowledge in there and understand that when this specific acronym comes out, it's related to a specific kind of subject and not to a different kind. Now, very briefly, to get how is this all working? Let's say that we have this sentence, which is like a query from a human, and it's saying like, well, I'm searching for something, and this is the sentence, like, on how to improve running by Scott. This is what somebody is potentially looking to buy a product from your website, and it's typing that. Now, how full text work is, it's going to process this. And the first step in Lucene terminology is like tokenization and analysis. So this input gets processed, and we know we're assuming here English. So I'm using a specific analyzer from the language, from the Lucene library, which specializes dealing with English language. And this is how it's going to break up this sentence. So the first thing you will see is, well, on is gone. Like that's something that's really not valuable, or it's not really giving me a hint of what you're really looking for. And then how, okay, the how is good, so we'll keep that. The to is also to removed. Improve, that's split up, and this is the stem. So it's applying natural language rules for specific, considering this is an English input, and it's taking the stem out of it. So the point here is that I am recognizing that this improve is actually the improve concept, and in my specific field of application, I'm not interested in keeping the information around to know that this was specifically the word improve, but I'm more relating it to the improve stem. So this is going to match other declinations and variations of the same concept within my index. Same is happening with running. Running, we take the stem out of it and it's run. The by is removed, and Scott is lowercase. Well, that's lowercase here because I'm just using the English standard language, and it's not applying like an entity recognition framework, which you might also use in this kind of context. And so it's not really treating Scott as a specific name or something. It's just another token. Now, the next step to build a full text search engine to recognize and extract valuable information out of it is the scoring step. Now, for scoring, I'm not going to dive in details, but Lucene has many different approaches on how to compute score, and you can basically choose one which works best for you. The default scoring, generally, they will apply a strategy like this. So they will look at each of these terms in their own, in the context of the input string, and they will give it a specific score to each of these terms, which is related to how these terms within the index are frequent and how their relation is with the overall number of terms and frequency. So in this specific case, let's say that we are dealing with a library of running books. That means that, well, how is probably going to have a low score. Run is probably also a low score. Improve, let's say, I don't know, I have no clue. Scott is probably, you know, maybe there are very few books which are written by somebody named Scott. I don't know, maybe it's very common name about authors, but let's say that there are very few books written by Scott. So it's going to do just comparing these factors. It's going to say, well, Scott is a term which I only see like in 5 books out of 1,000,000. So that gives it a high score. When it's computing all these together, it's going to compare these scores with each other. And it means that books which have Scott in the name are more likely to be on top of your results than books which have how in their name. See where this is going. Now, the exact formulas are well, it's probably best starting to taking the defaults, but you can completely customize those. Now, we're getting in details of how Lucene works, and so a little introduction of Lucene. Well, it's a very popular Apache project. It's written in Java. You can find ports in various other languages. I think, well, Python, the Python one is quite popular. You can find one in C#, and actually, I think there was one in Ruby. I'm not really following there. Some of them are very actively maintained, and some of them are a bit less maintained, but the reference is in any case Java. There are lots of excellent contributors working on it, and the pace of improvement is really impressive. And it's not a novelty. Like, this is not hype from last year or so. Lucene is being very actively developed since more than 10 years, and I think it's one of the most active projects since ever. Now, how do you get started with all this as a Java enterprise developer? Well, I will assume that you're familiar with the JPA standard, which is pretty much how you interact with databases. So storage, where you're storing all your information. That's a relational database. Now, something is missing here, because the relational databases are really bad at dealing with this kind of problem. So I'm not saying it's impossible. Many databases actually implement specific functions which do full text, and some are even quite okay. But each of them have their peculiarities. It's definitely not a standard feature of SQL. And even if some of these are pretty okay, the point is Lucene is really excellent. So maybe, in some cases you might want to settle on just using the one in your relational database, but you'll have to use probably custom stored procedures, no way to do proper pagination in some cases, and anyway, you're going to put a lot of additional load on your database, which is probably your most expensive piece of hardware and the hardest components to scale up in your system. So there are many good reasons to use Lucene. The problem is you're facing a very new aspect in your system. So normally when you buy maybe equipment for a typical deployment, I've seen recently you go on the Dell website, and I had a pretty good idea of what kind of server we were needing. But it's very hard to find one which is fitting, this intermediate kind of role. Like either you buy a machine which is like that was designed to be a relational database, or you buy one which is designed to be an application server. It basically has no disk storage, or very slow, and maybe maybe redundant, but very slow, ineffective, and rotating, spinning all disks in there. While what you want with Lucene is probably a solid-state drive. And so unless you go for like custom builds or go for very specifics, or get the phone and talk with some vendors and say, I need you to customize things a bit, you're getting a bit out of the usual, I would say. Like this is not what you normally do as a Java developer. So let's introduce you to Hibernate Search now, so that we can get to actually see some code in action and get it a bit in practice. So the first thing you have to know about Hibernate Search is you just have to add it to your class path, and it will completely bind in the lifecycle of the entity manager. So if you're using standard Java Enterprise JPA, but the underlying implementation is Hibernate core, then you can use an entity manager which has additional capabilities, which are like the Lucene integrations. So the quick start really is about make sure you have this additional artifact on your class path. And well, this is the last version. We just released it like yesterday. And it's the candidate release to be compatible with Hibernate 5. Hibernate 5 is currently at candidate release 2. I think it's just going to be released like that as final, but we're still giving an opportunity for people to make sure they don't need more changes. As soon as that will be final, the Hibernate Search ORM will also be final and released. And well, you could use Hibernate, native standard interfaces, but if you want to use JPA, you will need to add the Hibernate Entity Manager component explicitly. Anyway, the point here is on top of your typical dependencies, you just need to add this one to class path, and your integration with Hibernate Search is done. Like it will be picked up automatically. But what's next? Let's take a very simple model. Here we have an actor entity, and we're just modeling its name. So name and primary key. Now, if you want this to be indexed, to be taken in consideration for the Lucene index and be able to do full text queries on top of it, you have to add the indexed annotation on top of it. This is an org Hibernate Search annotation. And then, so that makes this entity being picked up by the engine, okay, and monitor it. Like for changes on this entity, they will trigger potential changes in the index, and it's going to, when you make a change to an entity and then at some point you're satisfied with all your operations and you're committing a transaction, this will have Hibernate flash changes to the relational database, and then Hibernate Search also will apply changes at the index. But in this case, nothing is indexed, so you also should choose what you want indexed. In this case, of course, name is the only option we're having. So we're keeping it extremely simple here for the quick start. Now, to add the relation, let's say we are having DVDs in our database. They have a primary key, a title, and they have several actors which play in each of these movies. Again, very simple. You make it indexed. You might want to search on a title, and you can also search, recursively within the relations of the same So this is going to include in the index of DVDs the fields for the actor. How does that look like? This means we'll get two indexes, one for actor, which will have encoded in the index. It will have ID, so it's able to match the name back to the primary key within the database. And then you'll have an index for DVDs. Now in DVDs, you'll have also the title, like we have mapped it here. But it will also have these actors, and then we use this dot notation, actors.name. Now here, things start to become a bit different than in a relational world. I have put a little star here to put a warning. But essentially what happens here is this is not a table anymore. So this is a multi-valued field. Like here we are storing the names of each of the actors which are in this relation from the DVD. So in this case, we have the movie Melancholia. There are these three actors, among others, which I didn't include in the example. But so this is not a flat relational table. And this will match, if you're querying by, let's say, actor's name, any of these. Okay. How do you query that? Essentially, what we do is we allow you to run any kind of Lucene query natively, because Lucene is extremely flexible, has a very vast ecosystem of extensions and add-ons and additional capabilities, which I really don't want to build an API and seal it off from you so that you cannot use all those the richness which is in the ecosystem. So in this example, we are assuming you're searching on title and actor's name, and you use that to build an org Apache Lucene search query. So that's a native class from Lucene, of course. Then you transform your entity manager in a full text entity manager, and you just use this little helper here, which extracts the more powerful version out of your running entity manager. So this could be an enterprise Java bean, right? You are just injecting your entity manager, and then you run this little utility. Or you add some CDI producer, which will create full text entity managers right off the box. Now what happens is that this full text entity manager has additional methods which you won't find on the standard entity manager API. It extends the standard entity manager API, of course, but one of these methods is create full text query, which takes a Lucene query API, a Lucene query instance, and some target types, so that you can target multiple different types and have a bit of polymorphism in there. And it will return a full text query instance, which is an extension of javax.persistence.query. And from there on, basically, you wrap it, the Lucene query, into an entity manager kind of query. And from then, you can use the normal JPA API. You can even pass it back to other methods which don't know anything about full text, and they will do like pagination. Maybe you have some methods which take a JPA query and make some nice rendering of some page. And of course, these entities which are returned from the index, they're actually managed entities, so they are within the transaction context. You can make changes to them, and when you commit, these changes will be committed back both in your relational database and in the index. So I'm going to show you a very, very simple demo. Normally we do rich demos with graphical things. In this case, I created the minimalistic demo, which does not have any interface and just shows how little is needed to get started. So let's start from the POM. Sorry, the resolution is not the best for Eclipse. So as we said in the quick start, you have the Hibernate Search ORM dependency, you have Hibernate Core, Entity Manager, and you will use JUnit and HDO for the tests. And we also need a Transaction Manager, so we go with latest Narayana. That's it. Dependency is done. What else do you need in an application which uses JPA? You need the persistence XML. Well, this is optional, of course, but just to make it explicit, we're using Hibernate here. Now, since we're using a in-memory database, I'm going to ask Hibernate create a tables when you're started. Now, use this data connection, and you can see there is absolutely nothing here for Hibernate search. There are, of course, many tuning options and properties which you can add here, like I want you to store the Lucene index on a disk, and where, in which path do you want me to store it, and lots of performance tuning options, but they're all like optional. You can deal with that when it's time for that kind of tuning. And so that's it. You just have your normal persistence XML. What do we have in the main? We have one entity, which is the tweets. The tweet is a very simple entity which has an ID, an auto-generated ID. It has a message, and we're going to index that. It also has, let's say, a sender. I call this sender the author. And we're setting here that we do not want to tokenize the author because, well, in the Twitter world, the nickname is basically like a keyword. I don't want it to go chunking and lowercasing and splitting on specific words. So just keep that as it is, but allow indexing on top of it. Because the default would be analyze yes, so that we can do the clever language analytics on top of it. And then we have a timestamp, and we're also indexing that. And we're explicitly saying we want to encode it as a numeric field, which is a more efficient way in Lucene to do range queries, so that you can select some range within your index and see some things. Now, actually, numeric field would be redundant here because for a numeric type, numeric field is actually the default now. And on top here, we're going to be back later on analyzers, but basically here I'm defining that this whole entity needs to be processed using an English analyzer. And what is an English analyzer? The definition is right here. You could normally put it in a separate entity or something so you can reuse the definitions. Anyway, this English analyzer is defined like this. So it takes the standard tokenizer, and you will have the Java doc in Lucene telling you exactly what the standard tokenizer does, but essentially it looks for white spaces, cuts text on the white space, and returns different tokens on each of them. And then we're going to run an ASCII folding filter on top of that, which means try to fold all the different versions of internationalized characters. Let's say you have an O with a specific accent on it, transform that in just an O, because we want to normalize things to normal ASCII characters. And we want to lowercase things, and we want to use this stop filter factor, which takes some properties. So that's this other property which we have here in the project. Again, this properties file is, of course, optional in the project. It's here just because I'm showing you how a stop filter factory can be configured. The stop list is a list of terms which we want to be ignored when we're processing language. This is not really required, but it helps, especially for English, to take out these words. And that's it. Then we have an implementation here, which does some full text queries. So this is how it looks like. I have a couple of helpers, like the query builder, which looks up the query builder for a specific type here, for a tweet. And then we build messages mentioning a specific keyword, create a full text query and return the query, or messages by someone. The difference here really is nothing, but it's on a different field, and this field happens to not be analyzed while this is analyzed. So we have some unit tests here, which you could run. Okay. This is, of course, in GitHub. I hope it's still green. You can see it. Yeah, it's green. So from here you can see what I've been doing actually. So very briefly, we have this before section which prepares some data. It starts the persistence unit from the persistence XML we created. From the entity manager, it creates a full text entity manager here. It makes sure that I don't have leftovers from a previous run of my tests because I'm storing this on the index. And then we store some tweets with this text in there. So you can see I'm mentioning some projects and products and some names from Jboss projects. And now if you remember how many of these are mentioned here, you can verify here, okay. Essentially, how many projects, how many times did I mention rules? And the query, which we produced before, will result 2. And we know it's green, so we can check what it is again. This is checking on the message for the keyword, creates the query. So I hope that's very familiar so far. And then we try again with this kind of rules. Now this is what I meant with this ASCII folding. So we applied some massaging of the input text here. Of course, you can go completely crazy and you can go with sentences, and it's not, Lucene doesn't just do keywords, it can also work on phrases. So you can work on positional scoring that like these 2 names need to be in a specific sequence. It's not valid if you turn the sequence around. It's okay if there are up to this amount of nouns between the 2 terms, and all of these things are customized. So back to the slides here.
How do you tell it about order? You just said the names of the query.
Yeah, it's a different kind of query basically. And here we're using just keyword queries, which means just look for specific terms. But you also can run a phrase query, or I'm actually going to show some different kind of queries right now. I don't have an example for phrase queries, however, but it's just a matter of using a different method on this.
For the Amazon thing.
Yeah.
The Amazon thing where the user doesn't put a name in
It would make sense to use phrases. Yeah.
The phrases on the
Probably. Now, what happens in practice is that very often you can actually combine multiple kinds of queries in one. And it's also going to, like, if you do a query and say, like, I want you to run this query, and then you do a Boolean operator with this other query, it doesn't have an operator or for Boolean, but it has the operator should, which actually combines the scores of the 2 subqueries. So you can tell them, for the Amazon input, for example, I would guess that you're using different kind of queries, so that like a bit of phrase query, maybe with a higher boost, but also like some fallbacks with maybe lower boosts. But it's always better to show you the book, even if you had the order of terms in the wrong order, than having you going to buy in a different place. Right? So by combining them, they make sure that if there is a book which matches exactly your order, that's going to be on top. But you don't want to discard the other results. You just want to downscore them a bit. So you can play with combinations of all these. So it's when we come to an entity mapping, where is my tweet? Something that is often useful is actually here to define the fields annotation, which takes an array of annotations fields, so that you can even store the same property from the entity. You can store that into multiple fields with different options. So you can, for example, tokenize this in 2 different ways and apply different techniques on top of the same properties.
So Sani, we have another question from the live audience. So Hamid Singh, so I apologize if I didn't pronounce your name right. He says, in this, you're using Apache Lucene using Hibernate, but from where should I start to learn Apache Lucene?
Okay, yeah, fair enough. So, well, if you want to start learning Apache Lucene from scratch, then there is an excellent book from Manning, which really starts you from Lucene. We are going to do a bit more with Lucene sooner, but essentially here we are exposing the same concepts of Lucene, we're exposing all of the query capabilities of Lucene, but we take away the complexity of people needing to learn how to write in the index, because writing in the index actually requires you to be very clever in how you handle these resources when you flush. And the primary problem is you cannot have multiple index writers open at the same time. It's not transactional, and you can quickly get in performance trouble if you do it the wrong way. So basically, we take out the complexity of writing to it. But if you really want to do it yourself, I would go with Lucene in action from Manic.
So the heavy lifting is done for the indexing side of things, but the actual search side,
yeah,
you basically just pass straight through to the Lucene, and that's a good search API. So
well, we also remap the results back into managed entities.
Right. Okay.
Optionally, you can also use projections, which means forget about the entities, just give me the arrays as they are coming out of the Lucene index.
Okay.
It's using TF-IDF stores.
Yes, that's the default.
So it has to pre-scan your full document cores to actually build.
Well, the scores are encoded in the index at indexing time. So that's what makes that's what makes indexing hard to do right, to get a good performance out of it. Because all these scores need to be computed. For every single write, every single update needs to update several global statistics, which they're actually not global. Sorry?
You got a secondary database to generate with all
yeah, so Hibernate Search works listening to events. So it's going to just apply the single update from the specific transaction right on. But it also provides a mass indexer function, which is like, let's say I start using search today, but I have an existing database which has lots of things in there, or I'm just changing all the mapping of how I want things indexed, then you will need to rebuild the index. You'll invoke this mass indexer. Could take some hours. If you're
Talk earlier about not using the relational database according to one of the reasons you gave scaling for.
Yes.
So the database tends to be a lot difficult to scale. Yeah. How does this scale? The index presumably is not running the database somewhere else.
Yeah. We're anticipating a good amount of slides here, but yeah, okay. Remind me if it's not enough what comes next. Just back to the slides.
So, sorry, before you go on, we have another question. So, is it possible to use Apache Lucene with MongoDB?
I'm not sure, but I think I heard of integration. There exists an integration. I'm not sure how well it's maintained, who is maintaining it, and who is doing it. But I think I heard of something. We actually do something like that when we use Hibernate ORM on top of MongoDB and Hibernate Search, but I don't think that's what he's asking.
We're having further questions. Can you repeat the question because the microphone's not working well for the audience?
Oh, sorry. The previous question was if there was an integration between MongoDB and Apache Lucene, which is. I answered I essentially don't know. I'm pretty sure there is something.
Yes.
So back out of the demo. That was the really trivial basics. Now we're going to see a bit more. Like this is just a paste out of the analysis configuration we had before, so we're going to skip that. The next feature we are having is the filtering. So in Lucene, it's very easy to pre-filter all your data set according to some criteria. So for example, if you want to show just all the products which are not suited for minors, you could define that as a global filter, and you can easily stack that on top of other queries. You have a usability improvement in your code here because it looks a bit nicer, but you also have a very effective performance improvement here because these filters can be cached, they can be reused across various queries effectively, and they can also be stacked in a very effective way when you have multiple of them that you want to apply in the same. So you could proceed, for example, having, well, some more filters on there, and filters can take parameters. So I could say here, I want the minors filter, and also apply the special day offers for this specific day, which is today, and also only for things which are actually in stock here at Newcastle. So you narrow down by subsequent criteria applying these. These are just like bit sets applied in memory, and only what's actually the end result is considered for the end final scoring. So it saves a bit of computation to do it this way, and it also looks nicer from a programmatic point of view. Another feature which is very common or to need in this kind of developer is this faceting. So faceting relates to this box that you have on the left when you're looking into Amazon. So in this case, we did a query on Amazon for Hibernate Search, and so apparently it has a good search engine in there because Hibernate Search in action is like the top result in there. But at the same time, it's also showing you on the left a categorization of these results. Now, this is another thing which is very complex to do on a relational database. If you just want, let's say you're building an application like this, and somebody tells you, can I have these numbers like in Amazon? When this question comes and you're building on a relational database, that's very hard, but this is very easy when it comes to using a full text query. More like this is a similar operation. So let's say you have an entity that you found, that you have found already. Like this is popular like in wikis. You're reading a page and you want to know more about the same subject. You don't want to go and specify what is the same subject of this page. Again, you just want to hit a button, like more like this. So that's what the name coming from. And in this case, we have it mapped on top of entities again. So the example here assumes you have an entity already, let's say some coffee instance. Then you can take our query builder. The query builder is just a helper that we provide on top of the Lucene native APIs, but you could use Lucene native. Now, and then we say, okay, we're going to start a more like this query, comparing all the fields. You could narrow down, you could list which fields you want to take in consideration if there are some fields which are better ignored. And then you can say, well, I want everything which is similar to this instance, and we're passing the ID here. Create a query, wrap it in a JPA query, and list again. Oh, sorry, I'm using the Hibernate query here, but it's the same. And you will get back a list of coffees again, scored from top to bottom, from the most similar to the one that you just passed in. Where similar means keeping in consideration all the fields which are in there with their specific scoring in the global, let's say, namespace of coffees that you're having. Spatial filtering. This is very nice. Let's say you're building a search engine and you want to give your users a capability to search for something, but narrow it down to a region. So we provide spatial mapping annotations now and spatial queries on top of that. So you can combine a spatial restriction with full text restrictions. So we could say for like tonight, I want an Italian pizzeria. Maybe you even have some name, and you just junk the name in again. So that's full text, right? You don't know exactly the name of which pizzeria, or maybe you forgot, or maybe you misspelled it, and the system has to guess. But of course, you don't want all the pizzerias in the world. Like you want to narrow it down, let's say downtown Newcastle, and that's the results you want. So it's going to apply first filtering, and how it works is like in this picture. It will first narrow down the big chunks using boxes. That's very easy and very efficient to compute, so it doesn't have to do radius computations. And then in the gray areas where it is really close and could be borderline, like the smaller box in here is okay, so it doesn't have to do computation, exact computation. And here in this other area, we're going to do an exact computation to give you like a circular range. So how do we run this on WildFly?
Well, how does it know what's spatial in terms of that pizzeria? How does it know?
Well, you will need to have encoded spatial coordinates with the pizzerias that you have listed in there. So once we have coordinates, you can give them as pairs or as longitude-latitude pairs. There is a longitude annotation and a latitude annotation where you can have coordinates interface implemented. then we index those coordinates. You can have, and that builds up a specific kind of index built on numbers, and then you can do effective ranges on top of that.
So you mentioned earlier it understands English, so it can do things like stemming.
Yes.
Is it smart enough to do that across domains? If I give it a place name, instead of stemming that, can you convert it to that place's geographic coordinates?
Well, you would need a database of coordinates.
Yes.
If you have that, yes, why not? I would love to make a demo like that, but I never found a database which gives me, address to coordinates in a spatial world. I guess there might be some privacy things that I cannot find out on the internet. Okay, so let's move to the WildFly part. I don't have much to show here because it's actually too simple to be proved. So Hibernate Search is packaged within WildFly. It's there already. All you need to do is enable it. So when you're deploying an application, you need to tag in your application using the Jboss models infrastructure and WildFly. Hibernate Search is there, but is not exposed to your application unless you ask for it explicitly. So you have to add one header in your manifest file to say, yes, use Hibernate Search. It's disabled by default. We're thinking of changing that. Like, we can look into deployment and say, okay, this application looks like it needs Hibernate Search. Let's enable Hibernate Search. The reason why it was not enabled so far is to give you more flexibility on which version of Hibernate Search you actually want, since we are doing a lot of development in community and with many new nice features coming up every month or two. I would prefer you to download the latest version of Hibernate Search, and with how models work in WildFly, you can have as many copies of the same library in different versions in the container without having conflicts. But so that mandates you to say specifically in your application, well, which version do you want to use? That's the only trick, right? But I'm going to show you how a test looks like, which is running in WildFly. And this is not a new test. I'm actually pointing to the integration test which we have within the source code of Hibernate Search itself. The low resolution is not the best. So if you check out from GitHub, organization Hibernate, there is Hibernate Search, the repository. It's a Maven project which you can just import in any IDE without needing any kind of specific setup. It will just import. It doesn't need any specific Maven repository. Every dependency is in Maven Central, so you're really just one checkout to go. Now we have these Archillian tests. So an Archillian test in the code base, this is of course a specific model because we don't want normally to depend on Archillian and WildFly and all of that, but there is a model which is called integration test / WildFly. You can find many interesting examples in there. It's using a shrink wrap to create persistence. Yeah, it's also creating the persist XML, but it's creating the definition of the wall deployment. So in this case, shrink wrap is creating just a Java archive, adding itself in there. Sorry, adding itself in there here, and it's adding the model, the NAGB, and some additional resources to there, and it defines the persistence XML, and we are using CDI. So to enable CDI, I just need an empty beans XML file. This defines the deployment. Sorry, scrolling back and forth. Now, what I wanted to show you is we're not including the dependencies of Hibernate Search in here. We're not including any dependency, actually. So this deployment just has the persistence XML, the means, and these three classes. And it's able to index, use all of JPA on top of this entity, and also using indexing. That's because all of Hibernate Search and also the Lucene extensions, all of those are within WildFly already. But what you need is this manifest. So in this case, we have an error which is containing the EGB. It could be simpler. I could have chosen a better test. And there is a manifest MF, and there is a string in there which you need to write. In this case, we're using a helper because I want to inject, variables which depend on the specific build from here. But let's open the documentation so you see exactly what's in. This is the line that you have to have in your manifest file to enable Hibernate search on top of WildFly. If you don't like adding the manifest, you can have a Jboss deployments XML file, which is a bit more powerful but is more verbose. You will need to paste all of this in there. In many cases, you will already have a Jboss deployment structure if you want to do some advanced customizations of other things. So the important thing is really just that you add this model and have its services exported. Back to the slides because we are a bit late. Aha, so there is a catch in all of this, which is what I was mentioning before, like when I was telling about I couldn't find a good, off-the-shelf suite server to do my experiments on it. The catch is, of course, that okay, now we have seen that having Lucene gives you lots of benefit, but the catch is now you have state, and you have an index which needs to be maintained, and it needs to be stored somewhere. And it's for best to be most effective, it needs to be stored within the same server which is running your application itself. So that changes a bit of the landscape of what you're expecting from your server configuration and maintenance. I would say the people who are running and maintaining your servers will also have, okay, like, now we need to be careful because these disks are actually high maintenance, so that we need to back up these things maybe. Well, the good news is you don't need to back up this because you can rebuild the index, of course, right? So it's not really critical. And now, but you have to understand some of these concepts. So you'll have multiple indexes. By default, we create a separate index for every entity type. And for this to be written by only one writer at the same time, there is quite some coordination happening within the framework. And this coordination, we call it like the writer goes, all writing operations go to a backend. And these backends are configurable. There are several backends which you can choose from the documentation. The default backend is just, Lucene, which means write it to the index right here on disk. Well, in the directory. And then you can play with directory configurations as well. So you have these two different aspects which you can combine in several ways. It's flexible, but not all combinations make sense, of course. So you need to understand a bit of this. So the default directory is, on Linux at least, it's memory mapped files on a file system. It's very efficient, but it requires some disk space. There are alternatives, like for testing, there is a in-memory in heap implementation. It's called run directory, which is simple, and in memory it's just a synchronized map. Surprisingly, at least for non-trivial sizes, the file system-based one is generally faster, more efficient in terms of speed. And we have an additional directory, which is the Infinispan directory, which means we can store all of that stuff within the in-memory datagrid.
Does that have a requirement about a single writer still?
Yes. So that's just a directory interface. The directory means it's the interface for Lucene to use to write into. And the Lucene at a higher level is expecting that he's the sole writer. It also comes with default lock factories, and you can override them. So we provide some clever lock factories to use in some cloud environments. But if you override it and get it wrong, and you put your own lock factory in there, and there is an option to say, like, I don't want locking because I know what I'm doing, and then you actually got the locks wrong, then two writers will happen at the same time. You'll probably end up with the corrupted index.
So with the Infinispan one, I'm imagining multiple servers sharing the same index talking to one database. Is that am I right in my understanding of what?
That could be a problem, and that's the reason why you can replace the backends. So in this picture here we have this is what we call this is the architecture for the JMS backend. The main idea is you pick one node which is in charge of writing, and all the other nodes which need to write will have to delegate to that first node. Just need some JMS queues in there. There are two catches. One is obviously the write to the index is asynchronous, like you're sending it to a queue the other from one side, and then you do a query. There really is no way for us to make sure that the write has been applied and the copy of the updated index happened before you do the next search. This is okay in most cases. Like if we are sticking to our example of the bookshop online, new stock arrived. If it's, I insert it in the database. If it's not on the web page in the same second, that's probably not an issue. It could be a problem in some other scenarios, so we have some different solutions for that. But you are going to trade off in other areas of efficiency or complexity of setup here. Now this is the first limitation. The other limitation is you need to set up these queues, and the master node here could be the point of failure or a bottleneck. Now, to solve the bottleneck problem, we said we have multiple indexes, and the picture for the backend applies to a single index. We can also do sharding of the same index. So like we do for every entity, you can have a different index. You can also have for a single entity spread it out to multiple different indexes. And this can be dynamic, so you can plug in your custom dynamic sharding policy. So that's the bottleneck problem. The failure problem, it really boils down to how you are configuring your JMS queues, the heartbeat between the masters, and this is basically on the roadmap now is to improve the documentation of how should I do that in practice, because it's a question which comes up frequently, and we're going to improve the documentation. But that's essentially how it works. Now, the next step is we don't do copies on file system of things, but you still have the backend delegating to a single writer, but the single writer writes on an index which is in Infinispan, and Infinispan is real-time replicated on the other nodes. So in this case, you get rid of the problem of asynchronous updates. It is, of course, more expensive on your network, because you have, for every single write here, you'll have events being fired to all the other nodes through the network. But so with this solution, you have all of them. So we're very late with time, actually. Going to be quick on this area. Since we started mentioning Infinispan, let's start with that. So Infinispan is this in-memory key value store. It is the core technology for where clustering within WildFly is based on. Essentially, it's an in-memory key value store, so you can use it as a map. You can use it outside of WildFly, and it understands transactions. It can offload some its state to persistence stores. We call those cache stores. It can be local or clustered, embedded mode, or server. We are using it when we're using it in the context of index storage for Lucene. We're talking about embedded mode. Now it has an additional integration, which is oh sorry, I went ahead. Yeah, we use it for many other things in Java EE, like it is a JCache implementation, and we use it for caching Hibernate entities in the container as well. Yeah, but the big one is it also supports querying within the datagrid itself. So in this case, we use still Hibernate Search. We're basing on the same library, but Hibernate Search is not indexing transactions of your domain being flushed to the database. It's indexing transactions of changes within Infinispan. So you make changes within Infinispan, and you are storing POJOs annotated with the same field and indexed annotations we have seen before. They will get indexed, and they will get stored within the same engine, and you get same or even better performance. So you don't have much new things to learn. This is how the dependencies look like. There is this Hibernate search engine, which is the shared project between the two. Infinispan core can bind optional to Infinispan query if it's there. Same way like Hibernate search can bind to the Hibernate search core and integration points. So the two side projects will provide the public API, and the engine is shared. The annotations are also shared, of course. And in both cases, you have access to native queries of Lucene. It's the same stuff. So here we are anticipating entity for an upcoming demo. Sorry, it's not an entity, that's the point. This is just a Java object which we are storing within Infinispan. So it doesn't have an ID, doesn't have the entity annotation, but still it will be picked up for indexing operations. And this is how you would store it in grid, right? This counter is the entity which I'm annotating, and you can store it in the cache like any other object. And then you can query it. It's very similar to what we have seen in Hibernate search. You do a search, get, extract the search interface out of, in this case, the cache, not from the entity manager, and then wrap your Lucene query. In this case, it's not a JPA query. What you get out of it, we call it, it's a cache query, and you can list results out of there. And yeah, I'm just going to skip this. This one is more interesting. So this is showing how you can get hold directly of an index searcher. So index searcher is a very low-level component in the Lucene stack. And here we are. If you're opening this one, you're not defining a query at a high level, but you're getting access directly to all the statistical information which is within your index. So on top of an index searcher, you can actually plug a lot of other projects which can do very advanced analytics on top of your index. So you just have to make sure that your input data is going to generate the kind of index that you will need to then run other kinds of analytics for this. How do you get started? I'm going to skip this. How much time are we having?
Probably 5 to minutes. That's
okay, yeah, can be done. So just a quick start for Infinispan is, in this case, I'm using Infinispan embedded, which is, to really use Infinispan, you would need several dependencies. This is like a catch. It puts together all dependencies for all the features for embedded mode. 7.2.3 final is the last stable version, and this is essentially how you start a new cache manager. You create a new cache manager, you get the cache from there, and then you use it. It implements concurrent hash map, so you really don't need a new textbook on how to use that. But you can configure it in different ways. So this default cache manager can take some configuration files. For example, the popular configuration option would be to have some persistent storage, so that when you're shutting down your Infinispan, you're not losing all your data. This is the same, but in a configuration API. And here is where it gets more interesting. So Infinispan is clustered, or local, but when it's clustered, it can be replicated, invalidated, or distributed. In a replicated mode, this is a configuration for starting replicated with synchronous replication across nodes. It means that everything you write will get this exact same copy on every node. So that's suited when your data set is not so large that it's going to overflow on the heap of each of your nodes. And you're more interested in, let's say, read performance, because if you get a copy of all your data on every node, it means that every node is going to be able to resolve get operations via a local hash map lookup. But every write is going to be expensive, because a single write means it's going to replicate this synchronously to every other node. The distributed configuration looks more like this, and it's not going to copy all of the data to all the nodes. It's going to copy every key, every entry to a specific number of nodes, so that it can ensure a specific, a certain level of availability. In this case of the configuration, we're having num-owners 2, and well, num segments refers to how the hash will is being segmented. But num-owners 2 means that every entry which is being stored in Infinispan is going to get to be replicated on 2 different servers. So if one server goes down, the other one will make sure to create a new copy somewhere. If both servers going down at the same time, you have lost data. And Infinispan supports querying. The first thing we implemented was using Apache Lucene, of course, which is what we show. But you can also run queries, of course, using traditional MapReduce. It can now also do indexless queries, and colleague Gustavo Nalle is working on Hadoop and Spark integrations for Infinispan. That's work in progress. So let's focus on the indexed configuration of Lucene. You have to enable it, and you have to pick which kind of strategy. And that's it. At that point, it's enabled. And here we're having some examples of these properties here. These are the same properties that are documented in the Hibernate search documentation. I'm going to skip to the interesting one, which is, well, here it's setting, this is indexing only local operations on the local storage on disk. But this one is using a custom index manager, which means an index manager is what manages all of the indexing aspects, so this is overriding both the directory and the backend and coordinating switches between backends and all the directory options. It's a big override. What this implementation does is basically it has the same basic architecture, but the master node is elected dynamically. And when the master node goes down, a new one is elected, and automatically every updates, every need of write is rerouted to the new master, which is applying all the synchronization operations on top of the index and re-replicating that back to the other nodes. So this is the simplest configuration that you can have for a clustered shared cache, shared index.
Can you get split brain where there's two masters?
Yes, but Infinispan has Infinispan core has some techniques which prevent the cluster to make changes when there is a split brain going on. So if there are no changes going on, there are no index writes, and so everything is stopped. Of course, that depends on which of these policies you are setting and if it's actually possible to detect the split brain, which is not always possible. Well, it's possible if you know the number of nodes in advance and you have that specified in the configuration files. So in terms of scalability from this picture, what you get is well, it depends on this Infinispan index is being stored in this cache. And so if this cache is being replicated, it means that every node here has a full copy of the index and is able to satisfy any kind of complex query independently without running any remote operation, remote call, right, RPC. If it's distributed, it means this index is very large and you're potentially downloading parts of the index during a query, which is extremely inefficient. So if you're having a very large index which does not fit in the memory of the single node, you probably want to configure also a cache store which offloads to local storage so that it doesn't have to do too much traffic. But you have to pick carefully between which clustering mode you're picking for the storage of the index. And also if you don't actually prefer to have every node having a full copy of the index on disk, which is a different option which we're working on now. More questions on scaling, John?
Is there any thought of being able to query the shards of the index in situ, so send the query to the index rather than bring the index to the query?
Yes. There is a feature which is, it exists already, but it's market experimental, which is called a clustered query, which does the opposite. So every node has only the index for the entries which it is managing, on which it is owning, and the query goes to all the nodes and then merges the results back on the invoker. It is a bit complex to maintain that code because it also does sorting and it does lazy loading of the different streams from the different nodes to make sure that this could be very large. So we don't want to fetch all the results from all the nodes at once, but you still want to guarantee the proper order between the results. So that's why it's still experimental. We also have a plan to completely change the architecture of this and take strong advantage of locality for the writes, so that actually every node will have local writes and no RPC operations on the write, so that there are no lock issues and no split brain issues on write operations, but then the output of the write is still replicated synchronously to the other nodes. That's coming. So focusing on this directory very quickly, I just wanted to say this, the Infinispan Lucene directory just depends on Infinispan core, does not depend on Infinispan query, on Hibernate search, or any of other of those components. So even if you're having an application which is just using native Apache Lucene, but you still want to store this index within Infinispan, that's possible without having the other dependencies. There is this catch, of course, that all this work that we are doing to manage the index writer and coordinate the different index writer nodes, that's, in that case, it's up to you to solve. You'll have to guarantee how you do this locking in a distributed way and keep in mind like split planes and all these concepts. Oops. Okay. This is the end. I have a very last demo. This demo was created by Gustavo Nalle Fernandez, who's a colleague of mine working on the Infinispan team. He created this. I had to run this demo in advance, so it's running already, and it's taking my CPU a bit of toll here because it takes several hours of downloads to fetch all the data. It has 10 million entries coming from this website, the NOAA government. It's harvesting all of the weather statistic information from 1901 to 2014, which makes of about 10 million entries to store in Infinispan. So I'm having a single Infinispan node running locally on the laptop here, which has been dumped all of this information, and this information is indexed via the annotations which we have known. I just need to get here. So input text. Here we have autocomplete. I did not load all countries. We only have United Kingdom, Norway, Brazil, and I think United States. You can try that out. So all what you're seeing here, the visualization here, is created by dynamic queries on the Lucene index, which is built on these 10 million entries which are stored in Infinispan on the laptop. It looks nice. Well, the zeros at the end, they just mean that there was no information for that, so ignore that. But for the rest, you can explore here, year by year, how the variation of temperature was in each of these countries. I'm just using the scroll bar here to move around. Oops. You can compare that with a different country. Brazil. See, when I click, and then the output comes up, that's where all the queries happened within the database. So that's a lot of data which is being processed right now. The trick really is, it's It's statistical information. It's reading it directly from the index. It's not a relational database, so it's using a better data structure to solve this kind of problem. And oops, I lost my demo display. Okay. Okay, so this demo is on GitHub. You can run it on your laptop. When you want to see it, make sure that you start a couple of hours in advance because it really has to download a lot of things. There is a configuration option, sorry, a configuration file. I have it running right here. Here you can pick which countries you're interested, and these two, you might want to set these to false the first time you run it. Also, start this JVM which has much heap which you can afford, because otherwise it's first time I didn't think about it, and of course it went in out of memory after some very painful hours of my laptop. It is storing all this data in a local cache, so after you run it the first time, you can rerun it. And if you look into the code in here, you will see just simple Lucene queries and a couple of aggregates, a domain being defined, which just defines which are the properties you're interested in, and then some code which builds this, the dictionary to extract this information. And the rest is, integration with REST and JSON to show some visualization there. Check it out. It looks very nice. So to wrap up here, what's coming on Infinispan? Well, we already talked about it, these improvements in indexing performance. That's the locality trick that I mentioned before. We're writing now a wiki page which is explaining exactly how we think to build that, and we're probably going to share that soon on the. These Hadoop and Spark integrations are coming, which are interesting because they are in the same ecosystem of Lucene. So when you start to have Lucene and Hadoop, that means you'll lock all of Mahout and other projects which are in this world. And what is being worked on right now is the capability. I've mentioned before, you can also run queries without indexes on Infinispan, but now it's only going to use indexes if all the fields you're mentioning are indexed. What is coming soon is the ability to narrow down results with what's indexed and then work on non-indexed form on the remaining parts of it. On Hibernate Search, we have much more coming. The soonest changes, we're going to upgrade to Lucene 5. Most of the work was done, so this should be ready soon. We really want to start experimenting more with delegating, not just with embedded Lucene mode within the same JVM, but also capability to synchronize all these changes which we're collecting within the the Hibernate session within the transaction and push those to Apache Solr or Elasticsearch, which conceptually expose the same kind of service as Lucene does locally. It's going to be painful in terms of API because we really like to expose all these Lucene capabilities, but it means we're exposing Lucene types all over. We probably will have to have like two different facades. It's just not possible to have both at the same time. There are two students working on the Google Summer of Code project. One is creating an extension for Hibernate Search, which doesn't need Hibernate, but just integrates with JPA. So that means you could, in theory, use Hibernate Search with other JPA implementors. It's going to be weird because of the name. It's Hibernate Search. But the part I'm most interested in is using a different technique for collecting the events. Like the JPA standard doesn't have a rich enough set of events being fired, which would allow him to collect correctly all of the needed events which are happening. So you would not be able to keep an index in sync just by listening to JPA events. Hibernate exposes many more events, so we listen to a larger set. So he's working on an approach which is based on database triggers, basically, which is interesting because it then opens other alternatives for us as well. But just look at the roadmap that I've updated it very recently. on our shiny new website. Here we have some more details. Of course, that's very possibly needing to change depending on what's coming up. Thank you. That was a very long run. Many more questions?
I think most of the questions were asked throughout the talk.
Yeah. Okay.
So thank you very much, Sane.
Okay.
Thanks for coming.
Thank you very much. Thank you. I forgot that all links here are hidden, so I will put